All right, hello, welcome back. So in the previous video, we talked about describing any arbitrary rotation in 3D using rotation matrix. Rotation matrix is great. It's very convenient to use, especially when you want to do things in computers. Matrices are perfect for that. The only issue with a few issues with rotation matrix. One of them is that the elements of that rotation matrix are not on them in themselves very meaningful. You cannot look at a rotation matrix and say, "Ha, that's how my system has rotated." Another issue is that rotation matrix in 3D is a 3 by 3 matrix. So it has 9 elements, 9 numbers, and they could be anything. They're all independent, not independent, but they could be different. But a rotation in 3D is essentially a 3 degree of freedom motion. So ideally, you only need 3 numbers to describe any rotation. And any of the remaining 6 numbers in the rotation matrix are kind of unnecessary. They're not independent. They are somehow dependent on the others. So this redundancy that exists in the rotation matrix is not helping anybody. So it would be ideal if we could kind of characterize a rotation by only 3 numbers. And thanks to Mr. Euler, I don't know if he had a doctorate or not, probably, maybe, I don't know. Euler, Uli, I call him Uli. We have exactly that. So in this video, we'll talk about the concept of Euler angles. So how do I do this? Let me write it down. Is it blue? My blue? Yes. So Euler angles. Euler angles. In general, Euler rotation using Euler angles is 3 rotations. Well, let me write it differently. 3. Oh, this I dug myself a deep grave. I don't know how to spell consecutively. Consecutive. 3 consecutive rotations about 3 axes in a specific order. I want to underscore this. Let me 3 rotations. I do these 2. So first, why a specific order? So one thing very important to note, and that's something quite annoying with rotation in 3D, is that order matters. So I have this book here. Let me come closer so you have a better view. I have this book, the textbook. So what I'm going to do, it is now facing, let me do it this way. Okay, starting with this. I'm going to do 2 rotations. First, maybe about the face, and then about the long axis. So the book is facing up. Oh, now I've forgotten how I started. Okay, now good. So it was this first face, then long edge. I end up in this orientation. Now let's reverse the order. First the long edge, then the face. So it is different. In general, you cannot go and arbitrarily change order of rotations. What you end up are different. So that's why order of these rotations matter. And what we have in Euler angles are three rotations with with the specified angles about the axis. So imagine, let me try to draw it. I don't know if I succeed. So let me do this with black. This is my original axis. So what I can do, let me label them too. Let's call this big X, black. Big X, big Y, big Z. What I can do is, what do I want? So let's look at a specific example. And this example is actually part of the educational process here. So every Euler angle, you need to specify a sequence of rotations and three angles associated with that. So what we have here in this example, I have a sequence Z, Y, X. What does this mean is, first we are going to rotate about Z. What we end up with is a frame. Let me do this. Oh, I don't know. Let's try this. Oops. So this is my frame. I have even labeled it for myself, so I know. Red one is X, Y is blue, black is let me do it this way. Black is Z. So what this sequence means is, first I rotate about Z. Then whatever frame I end up with, I rotate about Y, and finally rotate about X. So this is the sequence we are looking at, one rotation after the other. And we are rotating about the newly formed, every time about the newly formed frame. So if I want to draw that, so first rotation is about Z, which is Z of the big frame. Actually, no, let's keep it as just this Z, about maybe big Z, because I start with my fixed frame XY, big XYZ, and I rotate. So my X is going to come here. My Y is going to go there. Let's call it X prime, Y prime, and Z prime is going to stay the same. The second one, well, let me also, we rotate about Z with angle, what do I have? Psi. So this is psi. The first one is easy. And this one remains the 90 degree. Then we rotate about this new Y prime with angle theta. This one is going to be trickier. So Y is going to remain where it is. I'm going to rotate my X. It goes up there. This becomes new X double prime. And Z is going to rotate this way. Oh, not an arrow. That's fine. This is going to be my Z double prime, and my Y double prime is going to stay there. And lastly, maybe last rotation. Oh, this is my favorite green. Yes, that's the one. And the third rotation is about this x double prime with angle phi. So I forgot to annotate this. This is angle, what was it, theta. And now rotate about this new x. So y is, oh, it's going to be a little ugly, but this is going to be my final z. This is little z. And this one goes down maybe over there. This one becomes y, and this is my final x. So this is my final xyz. And make it a little nicer. Maybe it's not perfect, but I hope you get the idea. So this is Euler angle. This is the concept of Euler angle. You have to specify a certain sequence. So which axes are you rotating about? And three numbers, three rotations about those axes. So a few things is that there are many choices for the sequence, and they don't have to be just x, y, and z. Not all of them have to exist. I don't know, z, y, z is valid, or you cannot do x, x, y because it doesn't make a lot of sense. You have to switch to something else at a minimum. So this one doesn't work. You can also, this one is valid. You can also rotate, do three rotations instead of these every time newly formed frame. Instead of doing that, you can always stay relative to a fixed frame. So this big XY, big XYZ. So you can do X, Y, Z, or I don't know, Y. Can you do this? I think you can even do Y, X. You can repeat as well. Can you? I think you can. Yes. So all of these are valid. Either you can rotate about body frames, the newly formed body frames, or with relative to a fixed original frame. So just continuing on this example, let me be complete. So Euler angle are very easy to work with. First of all, you have all these nice interpretation of the numbers, rotation angles. And also it is mathematically often easy to work with because you know these rotation matrices. So R about, which one do I have first? So first rotation is about Z. And you know the 3D rotation matrix of rotating about Z is cosine of psi, what is it, sine? Sine of psi minus sine of psi, cosine of psi 0, 0, 1, 0, 0. You know this. Do I have enough space? These are about y prime. Again, it's a pure rotation about one of the axes, so it's the rotation matrix is simple cosine of theta 0 minus sine of theta. So about y, the sign flips to the other side. Sine of theta 0 cosine of theta, and rotation about this x double prime is 1 0 0 0 0 cosine of what is the phi, sine of phi minus sine of phi, and cosine of phi. And the total rotation matrix is, first you rotate about z, then whatever is left or you end up with, you rotate that about this y prime, and then you rotate it about this x double prime. And for this particular example, if you carry out the calculations, it's going to be long, so feel free to skip until I finish writing. It's going to be cosine of psi, cosine theta, minus sine psi, cosine theta, plus cosine psi, sine theta, sine phi, sine psi, cosine theta, plus cosine psi, sine theta, cosine phi, sine psi, cosine theta, cosine psi, cosine phi, plus sine of psi, sine of theta, sine of phi, minus cosine psi, sine of phi, sine of psi, sine of theta, cosine phi, minus sine of theta, cosine theta, sine of phi, cosine theta, cosine phi. So this is the rotation matrix associated with the Euler sequence ZYX with the angles being psi, theta, and phi. And for every Euler sequence, there is a different form of rotation matrix that you can always calculate using by hand, using the given the known rotation matrices about pure rotation about a single axis. And but you can also, I don't know, Google it, and somebody has probably calculated already, and it's somewhere on the web. So this is how you can do Euler angles. The other thing is maybe a couple of notes. So let me put it here. A few notes. Let me go to here. Notes. So these Euler angles are good choices for generalized coordinates. So imagine if you have a 3D, a rigid object in 3D. So you have 3 rotational degrees of freedom. To have generalized coordinate, you need to choose 3 coordinates. And these Euler angles are actually very good for that. And that can be quite useful when we derive equations. Another thing is if you can construct your Euler sequence. So you can specify for instance here the sequence psi, theta, and phi. See what rotation you get. Or let me write it this way. Get rotation matrix. Get rotation in general. You can specify what rotation you want in terms of these Euler angles. You can also go the other way. So if you know before that, so for instance, these are the coordinates for 3 joints of a robot arm. You can specify each motor to rotate a certain degree, and your robot will move somewhere. The other way around, if you know your rotation matrix, you can calculate psi theta and phi, so you can see what angles you need to be able to generate that kind of rotation. So this one has a little caveat that we'll see later. There are particular cases that you cannot actually do that. You cannot go from a known rotation to find the Euler angles. But in general, you can most of the time do that. Let me see if is there anything else I'm missing. No, okay, that is all for now. In the next video, we will actually see where you cannot do that and why. And that is very easily visible when we talk about angular velocities. So until then, I'll see you soon.